So this quantitative acid-base part 1 is an introduction to the concept of the effect of ions on acid-base balance. The next video will discuss a little bit more about how this works and introduce phosphorus and albumin. This is called quantitative acid-base chemistry, non-traditional approach to acid-base chemistry, Stewart's acid-base chemistry, Finkel equations, strong ion approach. It's called a number of things. But what is different about it is that it uses a number of different independent variables to explain hydrogen ion concentration and bicarb concentration. So the Henderson-Hasselbalch equation explains the acid-base balance only in relationship to CO2, bicarb, and H+, and does not distinguish which one of these is regulated by the other. And in the non-traditional approach, PCO2 is the only independent variable because it is the only one in this threesome that is independently regulated and affects bicarb and hydrogen ion concentration. And again, here is the equation that explains the relationship of pH to these two variables. The quantitative approach, on the other hand, views all of the following plus PCO2 as independent variables. And it is only taking these into account that you can fully explain everything that's affecting the acid-base balance of the animal. And we're talking chemistry now, and it's not always fruitful to use this approach in clinical settings, and we'll talk about that later. So we call it the quantitative approach. It won't seem quantitative at first, but using specific equations, it can help you quantify the contribution of each of these analytes to the overall acid-base balance, and it will help you understand the pathophysiology of the acid-base balance. But you're probably wondering, these are not acids or bases, so how can they affect the acid-base balance? And we'll get to that in a minute. This is from Stockham and Scott. It's the chapter that one of the chapters I uploaded in this week's module. I don't think that it's the greatest for reference. If you want to use it for reference, there are some good definitions in there. It's much more complicated in its explanation of strong ion difference from what we can cover in 1 week in this class. And so it might be overwhelming, but if you can ignore that part of it, it might be a good reference. So independent variables are the analytes that are regulated or they're changed independently of the others. So that includes PCO2, the strong ion difference, and the A total, which is we will explain, or I will explain later, but that's basically phosphorus and albumin, weak acids. The problem with bicarb and the hydrogen ion concentration in the Henderson-Hasselbalch equation is that they are not changed independently of the others. And PCO2 is, the strong ion difference is. And so then the dependent variables are those that change if and only if the independent variables change. And this is a different way of thinking about it because we tend to think about how H plus and OH are regulated. H plus and bicarb are regulated. But those are in fact, in this approach, dependent variables, and they are not regulated independently of the others. So clinical use of this, though, is really, uh, I think, only valuable when other things are not completely normal. So the Henderson-Hasselbalch equation is completely clinically useful and appropriate. So in other words, looking at PCO2 and bicarb and H plus all as independent variables, and using only that system. So in other words, looking at PCO2 and bicarb and H plus as influencing each other, when the weak acids are completely normal. I would also say that I think it's useful also to think about strong ions and the strong ion difference, even when these are normal. And hopefully that will become clear later. And I want to emphasize that this is about metabolic disorders, not about respiratory disorders. The PCO2 is in fact an independent variable, but the way we evaluate respiratory disorders does not change in between traditional and non-traditional acid-base disorders. So Stewart was one of the first investigators to come up with this system of evaluation. This was a long time ago. We act like it's new, but actually it's been 30 years now, I think. And he mathematically showed that strong electrolytes and weak electrolytes can actually affect the hydrogen ion concentration on its own. And he did this by solving for electroneutrality, considering strong ions, maintenance of the dissociation equilibria. And that means that even water will dissociate in very, very small amounts at pH 7 to the hydroxide ion and hydrogen ion. So it can be explained by a dissociation constant, Kw, which you can see is very, very small, but it needs to be taken into account. And then also conservation of mass. So here is the principle, and this is the main thing I want you to understand about strong ions. And I think this will help to view biochemistry, serum diagnostic profiles, etc., in the context of acid-base balance. So let's use chloride ion as an example. It's a strong anion. So if you add 1 ml of hydrochloric acid to 999 mils of water, you will have complete dissociation of H plus and HCl. In our freshman chemistry classes, we were told to calculate the new expected pH based on the amount of hydrogen ion added from the HCl and to ignore the chloride. So you would expect the pH to change only according to the H plus concentration. And here is the equation. So the equation for electroneutrality is H plus equals the concentration of the negative ions, which is chloride and hydroxide ion. And you can already see that the hydrogen ion is greater than the chloride ion added because you need to include hydroxide ion. Including also the dissociation constant of water, which can be described by this equation here. If you solve for hydroxide ion, then you can see that the hydroxide ion equals the dissociation constant of water divided by H plus. So if you replace this for the hydroxide ion in the electroneutrality equation, you come up with this equation. And then if you solve for chloride, you have H plus minus the Kw over H plus equals chloride. Multiply both sides by the hydrogen ion concentration, and eventually, and it's not too important how you get there, eventually you come up with this polynomial. How do you solve a polynomial? Or you use the quadratic equation. So we don't really need to do this. This is not math, but eventually, if you solve for the hydrogen ion concentration, you come up with this equation, which should show you that the higher the chloride, the higher the H plus concentration and the lower the pH. I would not worry too much about this math. I am a math person, and to me, if I don't believe something intuitively, I will believe the math. And so this is showing you how this is derived, and I'm hoping this will persuade you that the hydrogen ion concentration is directly proportional to the chloride concentration, and therefore this independent variable influences this dependent variable. But let's look at an actual calculation. Okay, so this is, I say this is a practical example. It's not, it's just an Excel spreadsheet. But here is the concentration of HCl in moles. It's a molar concentration. And using our freshman chemistry, calculating the new pH based on the H plus concentration alone, this is the pH we would expect. And what are the rows? The rows are serial tenfold dilutions of HCl. And the bottom dilution is the one that is the closest to the concentration at physiologic pH. So what I want you to notice is that this is the expected concentration based on the HCl molarity only. And this is the actual pH if I input the quadratic equation solution solved for H plus. So the difference is less than impressive at high molar values of H plus or HCl, but at physiologic pH and physiologic concentrations of H plus, you can see that the pH differs significantly. So the expected pH is 6.96 rounded up. And it's much lower, 6.8, at physiologic pH. And again, numerically, this is not very different, but at physiologic pH, it becomes quite important. These differences are much greater. The whole purpose of this is to persuade you that strong ions alone can affect the pH of the animal. So here is another important concept. And if you only remember this, you'll be fine. So an increase in strong anions is an acid change. And I just showed you that by the previous Excel spreadsheet. Conversely, an increase in strong cations is an alkaline change. And an example of that would be sodium. The SID equals the strong ion difference. And the most obvious strong ion difference on our biochemistry profiles is sodium minus chloride. And so the difference is also reflective of an acid or alkaline change. So a decreased SID, which would occur with an increase in chloride, is an acid change, and an increased SID is an alkaline change. So think of a true hypochloremia, such as occurs with vomiting and loss of chloride. So the goal of both systems is to try to explain all of the relevant variables that control H plus in body fluid. And the quantitative approach is just an extended way to do this. So in the classical theory, the Henderson-Hasselbalch equation discusses or describes the relationship between CO2, H plus, and bicarb. But it does not differentiate between all of the causes. Stewart's acid-base theory evaluates the underlying physiology, including electrolytes and weak acids. And in some cases, it can help direct fluid selection. So I feel like I'm spending a lot of time telling you why we care about this. So learning about this usually requires, for me anyway, great mental effort. So I'm trying to tell you that the cost-benefit ratio is worth it. I do believe that this is for you to decide. And the proponents of this method agree that it provides a mechanistic view as to why pH is changing that fully integrates electrolyte and acid-base physiology. And Di Bartolo, which is a chapter that I've uploaded, it accounts for all the independent variables affecting the acid-base balance. So it is, if nothing else, it is a more complete way to understand the acid-base contributors overall in an animal. And personally, I like to quantify each analyte because it helps me understand overall what is contributing to the base excess or deficit of the animal. So what are the disorders that occur in the quantitative approach? Respiratory disorders, of course, because PCO2 is an independent variable. So we have respiratory acidosis and respiratory alkalosis. The differences start with the metabolic issues, 2 and 3 and 5 and 6. So we have a strong ion acidosis, and we've seen that with hyperchloremia, and non-volatile buffer ion acidosis, which is hyperphosphatemia. We have not discussed that yet. Strong ion alkalosis, which includes hypochloremia and others we'll get to later, and non-buffer ion alkalosis, including hypoalbuminemia. So these are metabolic changes that differ from how we discuss acid-base abnormalities simply by bicarbonate. So a decreased SID is a metabolic acidosis, and an increased SID is a metabolic alkalosis. Here's an example. I believe we've seen this cow before. 3-year-old Holstein cow, 30 days in milk. I'm not entirely sure, actually. With a right-sided ping, caudal to ribs, and pong cranial to ribs, sloshy viscera on ballottement of the right abdomen. She's tachycardic, 8% dehydrated, and has weak rumen contractions with ventral abdominal distension. So if we pretend she's a dog and do the calculations, we can see from her blood gas that she has an alkalosis, which can be described as a metabolic alkalosis because her bicarbonate is increased. And we can do the calculations to show that her change in bicarb can be quantified, and we can calculate her expected change in PCO2. So this is suggesting that bicarb influences the PCO2 and is actually an independent variable on its own. And we can determine then that there is a metabolic alkalosis with respiratory compensation. The quantitative method would describe this as a respiratory acidosis, a dilutional acidosis because we have a decrease in strong cations, along with a hypochloremic alkalosis. And this process predominates. And this can also be known as an increased SID alkalosis. So that's just two different ways of describing the same thing. And disorders of SID are also reflected by changes in bicarb or base excess. And in this case, these two methods are equal as long as this cow has normal phosphate and normal protein, which we don't know yet. So let me introduce these non-buffer ions. They are the strong ions that we've already talked about. Sorry, let me introduce these buffer ions. The non-buffer ions are the strong electrolytes that we've already discussed. The buffer ions, also known as atotal, are derived from weak acids that are not fully dissociated. The ones that we are going to discuss the most are proteins and phosphates. The one that I tend to focus on the most is albumin, and then phosphates are phosphates. So again, a list of strong ions. Now we'll start describing the ways in which strong ions can change. So strong ions can change with a change in water balance. And remember, this just means that there has been hypotonic, isotonic, or hypertonic dehydration. And so changes in water balance will affect the concentration of sodium. It will also affect the concentration of chloride. But chloride can also act on its own, as we have discussed. And then there can be changes in other strong ions, such as lactate and ketones and uremic acids. So let's just look at sodium minus chloride. So if chloride increases, the strong ion difference will decrease. So here's another Gamblegram. If chloride increases, the strong ion difference will decrease, bicarbonate will decrease, and we'll have an acidosis. If chloride decreases, then bicarb will increase, and we have a strong ion alkalosis. And we'll discuss this more in the next video. Other strong ions, such as magnesium and calcium, are regulated so precisely that we don't even discuss them enough. We don't even discuss them as being important in changes in SID. And you'll see in Stockham and Scott's chapter, if you read it, that they are also included in the calculations, but we are not going to discuss them in this unit. So I have a quick check that you can use. It's a case-based quick check just to get you checking yourself on what you have learned in this video using a clinical case.